so lovely to welcome you to Roehampton. My office is a much, much smaller room than this. Indeed, my lecture room is much, much smaller and grottier than this. We only ever get to use this for special events such as this. It's so lovely to have people back here on campus, though. Thank you so much for coming along to this. It is really almost impossible to follow what you've just heard there. I'm going to take something really very, very dull and explore this idea right from the start of early years all the way up to the end of Key Stage 5. So we're taking a single idea, really, for a walk here. And this falls under this heading of computational thinking. This is the golden thread that runs through England's computing curriculum. This way of looking at problems, this way of understanding systems, when we can bring the power of these machines to bear on this. So, you know, we solve problems lots and lots of other interesting, exciting and different ways, but computers are really very, very good at helping us solve a certain sort of problems, ones where we can bring some sort of computation to bear on this. As Jeanette Wing, who coined the term, computational thinking describes the mental activity of formulating a problem that admit a computational solution. We can start laying the foundation for this in early years and carry on with this approach to Key Stage 5 and indeed beyond. Barefoot Computing, brilliant CPD scheme and loads of really nice free resources there for teaching computer programming, computing and computational thinking throughout the primary phase. For Barefoot, we said computational thinking draws on a number of these quite distinct concepts, this idea of logic, that we can make predictions, that we set these machines up in a particular way, we can predict what they'll do. The sequence of steps, the set of rules that we have for solving a problem. Taking a big problem and breaking it down into smaller parts, looking for the patterns, looking for the similarities, playing with that. Moving to levels of abstraction. Is there a more general thing that we can look at here? What happens when we change some of this? And checking whether what we're doing is working or not, whether it's an efficient way of doing it. The right-hand side is just as important, but I don't have a huge amount of time, so I'm going to move on. There is a danger with this, though, that we end up teaching them, this is an algorithm. When we get them, you know, making algorithms for jam sandwiches, or we get them, what's the algorithm for a cup of tea, and so on, and that's fine. There's a place for understanding the idea of algorithm. But it's only really when we're looking for computable solutions, for solutions that can be programmed, or at least could be automated, that computational thinking comes into its own. We don't need to make those exaggerated claims that it will solve all of the world's problems. The coding really does matter. Without the coding, without the computer programming, computing becomes, as Peyton Jones puts it here, just a dry theoretical husk of a subject. And those of you who are struggling with OCR exam reference language up at GCSE may have some sympathy for his position on that. I see the computational thinking as a subdomain of problem solving. I see coding as at its best sitting within that computational thinking bit. At its worst, the coding is out and apart from that, and we just teach them, you know, follow these instructions, type this in, type this in, type this in, or do this, do this, do this. And look, you've made scratch, move across the screen, or whatever. That's not so much teaching programming as, I don't know, programming children, I think. So it is, as I say, the golden thread. A lot of the foundations of this we lay right in early years foundation stage before they get to the age of 5, and then it gradually builds up as they progress through the curriculum and the exam specifications, and you get things like efficiency and logic and abstraction there up in Key Stage 5. So what does this look like in early years foundation stage? Who here is teaching in reception or nursery? Excellent. Thank you both. Very, very good. So you've got a set of UK coinage. Come up with, do you remember coins? Anybody in the room remember? Used to use those before everything became sort of phones or watches or whatever. So you've got all of these coins left over from the old days. Give me an early years foundation stage, give me a reception class activity involving coins, please, either of you.
Shops.
Shop, absolutely. How much change do you get? Could you do that? Or at least you get some change. I'm told that these days when children are playing shop in nursery or reception, it's hold their watch against the till, or you just swipe the card. Any suggestions, sir? Okay. There's all sorts of things you can do without even worrying about the value of this money, if indeed this money still has value. You can sort them into groups there. You know, some of those are silver, some of those are sort of nice browny colour, some of those are a lovely gold colour to them. So we've got a sorting and classifying thing there. Most of them are circular, aren't they? Not all of them, though. How many sides have they got? Can you put them in order of size? Can you put them in order of weight? There's all sorts of sorting and classifying and objects according to their properties. Yes, we can start thinking about the value of those things, but there's just, as a thing, these have interesting properties that early years foundation stage can start playing with. How many of these weigh about the same amount of this, take up the same amount of space as so many of those, lots and lots of, what is it, non-standard unit type activities there. Did anybody spot the odd one out, by the way? Yes, what's wrong with the pound coin?
It's the old pound.
It's the old, I can't find a photograph of the current set. I could, I suppose, collect some of these. So we have there in development matters things which look a lot like computational thinking to me. There isn't really any specification for digital technology in the early years foundation stage, but it does have in development matters all of these things, which is exactly what Google are looking for when they're recruiting software engineers. Everything you need to know about computational thinking essentially happens in kindergarten, nursery, in reception classes. What have you got there? Goal-directed behavior, predict sequences because they know routines, a range of strategies to reach a goal that they've set themselves, correct their mistakes for themselves, keep on trying when things get difficult. Think of the classes you were teaching today. Is that not something you would aspire to for them? Keep on trying when things get difficult. So we lay the foundations for this. Key stage one, I think we get to be a little bit more formal. We start thinking of these coins as having value rather than just properties there. And you have this throwaway line in in year 2 of National Curriculum Mathematics that pupils should be taught, very assertive language there, find different combinations of coins that equal the same amount of money. Yeah? 12p. Give me a combination of coins that makes 12p, please. 552, that works. That's one way of doing it. It doesn't say find all different combinations of coins that equal the same amount of money, because that's a really difficult question. I think we could spend a little time thinking about those now. But finding one way of doing that is there, or finding different ways of doing that is there in year 2 mathematics. It has to be taught according to the Secretary of State. Bless him. And this is a thing which machines can do. Once when we were using money, you put the money into the vending machine, it gave you the thing, and it gave you the right amount of change. And a good vending machine would do that using the smallest number of coins possible. If you had 12p in change, getting 12 ones would have been really quite annoying. A 10 and a 2 would have been, I think, even a better solution than yours, so if you don't mind criticizing it like that. So we have an interesting problem here of what's the smallest number of coins that you need to make these amounts. And I'm just going to pick on people. The lady in the stripy trousers, please. 28 people, the smallest number of coins to do that.
4.
Tell me them.
25, 2, and 1.
Yes, that's exactly right. That's what I got. Anybody got it in less? Okay, so we could do that for all of them. I'm not going to take your time over this, but this is an interesting. I think this is like a key stage 1 type maths problem. What's the smallest number of coins you need to make? You're disagreeing with me, the lady in the blue top. No, is that allowed? Key stage 1 could do this. I think try it when you get to school tomorrow. I think they could do this. So that's your maths lesson there. What's the smallest number of coins to do this? For computing, I think we want to actually get them figuring out the way to solve these problems. Not just solve this problem and this problem and this problem. But is there a general solution to this? Can you think of a method which will give me the right answer to this, irrespective of the amount of money I'm trying to make? Is there an algorithm for this? I heard a yes. That sort of kind of says, what is it? Then please, that wasn't really an existence proof.
If and else statements, do some if statements.
Just talk me through, general strategy here. I don't want sort of fully formatted.
Okay, you have the 8 pence. So first of all, you see, you find the biggest coin, and if 5 goes into it, you take that off, and then you've got 3, and then you take the 5 no, so it goes to the 2 pence.
We call this a greedy algorithm. It's a standard method to take make as much difference to this as you can initially, and then sort of get smaller and smaller parts. It's kind of the minimum viable product as an algorithmic approach there, isn't it? So 48p. Start, I can't take a 50 off, but I can do a 20, takes me down to 28, I can take another 20, that takes me to 8. Then we've got that's a problem we've already solved, we've got a 5, we've got a 2, and we've got a 1. I think I can do that, I've lost count there. In 5 coins for 48p, something like that. Can't talk and think at the same time. But that algorithm does sound as though it makes sense. I think if you apply that to the 5 examples on the board there, we will get the right answer to it. I can't think of an amount of money where that wouldn't work. All right, so we've got an algorithm. I think the key stage 1, computational thinking, That's a really good point to get to. We've got a problem there in the maths curriculum. Not only can we do it over in our maths lessons and get answers, but we've also figured out a general strategy to solve all problems of that kind. I don't think Year 2 maths teachers ever say, this is the way to solve all of these problems. But children kind of figure it out themselves, because once upon a time they were used to working with coins, weren't they? So Key Stage 2, I want to implement that algorithm there as code. So you were already thinking about if statements, and I'm way ahead of me, write a program to work out the smallest set of coins to make these or any amounts of money. So we're moving from, we've got an algorithm, we've got a way of solving this in our head now, to now I can make this dumb machine do this for me. And that is really what we're aiming for. We have a way of solving it, and then we get to implement that as code. So I started off with a really very naive way of doing this. We get some input, how much money in pence. I'm going to keep track of the change I'm giving, but you don't have to do that. We set the amount left to whatever the answer is, keep repeating, taking off £2 coins until we can't do that anymore, give them a £2 coin, and then we could add in some more blocks. I think I can step out of the deck and start writing some more code in here if I wanted to, so just duplicate that, add that down on the bottom there. Now we've done £2 coins, let's do £1 coins. Here's, never do live demos of these things. Here's £1, change the amount left by 100p and so on. And so we could do this, I should work for any round number of pounds now. How much money in pence? Let's do 500 pence. £2, £1, oh, £2, £2. It didn't quite add the right thing because I didn't write the code correctly. Never do live demos. There's a lesson here, folks. Let's try it once more. If this doesn't work, we're giving up. £2, £2, and £1. He got it right, okay? We could try that with the others once we finish the code. And that's fine. It's going to take a little while to duplicate all of those blocks. I'm not going to do that now. Present. There we go. Okay? Because at some point we want to sort of step away from that level of detail of having to write that. And Scratch allows us to make our own block for that. So I can define, each time I was doing pretty much the same thing. I was taking off the biggest amount I had, reducing the amount left by this. So I've got now a block which does that for each of those. And I think that's much more elegant code. Getting your Year 5s, Year 6s to being able to write that independently, I think that's a pretty good goal for primary programming. You know, there are more exciting things you can do in primary programming than this. But getting them to be able to do this is not bad. We've got sequence there, we've got repetition, not got much selection going on, but I am sort of doing some sort of comparison statement there. Okay, so getting to that point by the end of Key Stage 2, that's all right, actually. I think you could cope with them coming in with that sort of skills. It's good. All right, so where do you take them next? What happens in Key Stage 3? Well, loads of P5JS actually would be a really sensible thing to do, but you might want to start staying in Scratch, staying in this really easy to use, intuitive programming language, and just extending the ideas, the computational thinking at this point. So we might start introducing some more sophisticated data structures. We might keep track of how many of each type of coin we've used there. We might actually use a list here as a way of iterating over the particular values of coins that we've got. So I can initialize my coins, clear out all of the coins I've got, and then just add certain amounts into that. And then the program on the left does pretty much what we were doing with Scratch previously, but we're using a more general data structure to do this. We're keeping a list of the coins that we have in the currency system and also drawing coins as I'm going along. And once you've got that happening, you start realizing, hold on, UK coinage is only one way of doing this. Other coinage systems are available. I could easily take this and make it work with euros and cents. I could easily take this and make it work with American coinage if I wanted to. So America, some of you may once upon a time have been allowed to go to America. They have this really weird coinage system there which has just these 4 values of coins. So if the only coins you had were 1 cent, 5 cent, 10 cent and 25 cent coins, what's your solution to, let's do the 48 cent question now please, Lydian's press.
25, 10, 3 months. No,
Yeah,
25.
Yeah, 25, 10, 25.
Oh, sorry, 3 months, yeah.
25, 10, that's 35, I'm aiming for 45 here, aren't I? Oh my goodness, 25 2 tens and 3 ones. Is that right?
Yeah.
That should work, shouldn't it? But this suddenly becomes a more, because we're not used to this coinage system, and it's a weird coinage system, it becomes a harder problem, doesn't it? And, we can write code for that. But all I need to do is modify that initialization script, rather than starting with UK coinage, start using US coinage for that and get the program to work out exactly the same thing. But what if our government decided to swap the coinage system to something entirely different? What if the coinage system was pennies, tuppences, 4 pennies, 8 pennies, 16 pennies? I don't know what's going on there. Yeah? If that was our coinage system, what would be our solution for 30 pence using those coins?
16, 8.
Go well, go well.
16, 8, 4, 2.
Yes, absolutely. A 16, 8, a 4, and a 2. Has anybody seen these numbers before?
Yes.
Okay.
And binary conversion system?
It's the binary place values, isn't it? So all we're doing here is taking a denary base 10 number and converting it into the binary representation of this. Children are used to working with coins. Well, they once were. Okay? If you change the value of those coins, you can get them converting into binary by just doing it almost intuitively. You don't really have to think about it once you see these as values of coins that we can use. And I've got a program ready written which will do that for me, because I just ask it to initialize with my, I don't know, I need a name for these binary value coins. Do you think, I don't know, Bitcoin, like binary bit? We could definitely call this Bitcoin. Let me see whether anybody's thought of that already. Okay, so I've not used any text-based programming here. I could have done this in text. Of course I could. And essentially they have to learn one text-based language. JS may be the way to go. But I've got them thinking about a problem in computation using a language that they're already familiar with. They may be already scratched out by this point, but they've not seen these problems and they've not seen this application of Scratch. So you don't have to go that way. For Key Stage 4, they will have to use text-based programming for staying on to do the GCSE in computing. They have to use weird, made-up, pointless languages like OCR exam reference language. Python is a really useful language to learn, though. So the program that I showed you earlier in Scratch, here is exactly the same program, just expressed as text rather than blocks. This is harder to do, because you can't just see where the blocks are on the left-hand side of the screen. You've got to remember things like indenting to show that that code only runs if this condition is met. It's much harder to write this, forget the expression, from scratch, than to actually write the Scratch there. So there is additional cognitive load. But if you're already working with a program that they know and understand, at least they don't have to think about how to solve the problem before they get on to actually solving the problem. Yeah? And we can do the same thing with our binary. We've got a converter into binary. If we do that, we can just modify the code, this idea of generalization of patterns, slightly by, instead of saying how many of the coins, what those particular bits are. And that's a really nice, intuitive way of converting from denary into binary using this sort of greedy approach to this. So that's pretty much as far as you want to necessarily get for Key Stage 4 GCSE programming. Where next? I promised you taking the idea all the way. Well, what happens when you take this up into Key Stage 5? Well, you can do what the AQA specification says and start introducing functional programming here. All of the ones so far have either hard-coded the values of the coins or have worked through a list of coins. What we have here is a function which calls itself. The number of coins to make a particular amount uses the number of coins with one less coin in the list. So we have a recursive approach to this implemented in functional programming. I'm not going to go into the detail because there's something much, much more interesting to talk about. So, is there anybody else in the room who worries now that we have got Brexit done, that they're going to bring us back to using pounds, shillings and pence? Feet and inches, 12 times table was there on the curriculum for a purpose. So imagine that they come along, I don't know, maybe for Christmas, and say, we think, now that we can do things our own way, pounds, shillings and pence, people knew where they were with that money, didn't they? So what if your coinage was 1 penny, 2 penny, 3 penny, Well, sixpence, sixpence, shilling, florin, half crown, crown, that's half sovereign and sovereign, yeah? What if those... I have the young people in the room. Look it up one day. So let's have a go at this. You know, Sir's greedy algorithm there made perfect sense, didn't it? So let's do 48 pence using this coinage system. So again? 224s. Absolutely, 2 florins, I think they would have called that once upon a time, yeah? What does your algorithm say you should get?
224s.
Right.
30. No, we did 30 first. We did 30. We've gone. Yeah.
Your algorithm says we give them a 30. It's like half, I don't know, half crown or something. We do a 30, and then a 12, that's 42, and then a sixpence, which takes us to 48. That's 3 coins. Whereas you've got some much better solution to this using 2 florins. I like your solution better than his solution now. So at Key Stage 5, I would like my A-level computer scientists to start questioning what went wrong. All the way up to age 16. Greedy algorithm absolutely works. Suddenly you throw this post-Brexit coinage back at us, and suddenly that breaks down. It's not, this is, you know, firstly, we cannot use our algorithm to solve this problem anymore. There is something about this set of coinage, and other coinage, is not unique in this respect, which breaks that algorithm. So have we got an algorithm that would work for this? Is this a computer? You got the solution. I can't think of a better one. How did you do it? And the machine doesn't know that. It can work it out very, very quickly. But this becomes a really hard problem. This is the point I'm kind of just waving my hands about making here. So yeah, we could run it through our code and we'd still get the wrong answer to this. There is a recursive way. You know, the functional programmers will get to it. So the minimum number of coins needed to make any particular amount is 1 plus the minimum of, the smallest of, the minimum coins needed to make that amount less £2, less £1, less 50p, or whatever, using current coinage rather than the old version. Coded as Python, it looks like that. I'm not going to walk you through the code, but something interesting happens when I attempt to run this. So here's my code. Reconnect. Any of you who are working in Python, I would really recommend Google's Colab as a lovely online environment for that. It's like a dialogue with the compiler here. So these are the ones, or interpreter here, these are the ones which we were doing earlier. Here is my recursive algorithm for this one that we did here. Let's run the code. It will connect to a Google Cloud server. And so how much money in pence? Let's say, okay, using the old coinage, make me 14 old pence. That should be a shilling and a tuppenny bit. Should be 2 coins. Oh, and it said that didn't work. So font time. Okay, I made a mistake in the code here. 14. Okay, let's just take that line out. And that line out. 14, testing it. Clearly not. And take that line out. Run the code. Third time lucky. 14. You need 2 coins. It gets it right. If I ask you the question that I asked you, which you got really quite quickly, 48 old pence, how many coins to make that? Run the code again. 48 old pence. And it goes off and thinks about it for a very, very long time. And there are Google server farms which are melting here. Some of you may have seen, like, the internet stopped working just before lunchtime. This was me testing it, by the way. Okay. So it works. It will get you the answer, but it takes a very, very long time because of the depth of that recursive tree. Is there an alternative? Well, what we did at the start, you got me the answer to 20, somebody got me the answer to 28, was it you? Okay. We could use that when we had to work out our 48. We know the answer to 28. So from 48, I just take off my 20 and look at the answer I've already got for 28. If you build up the answers as you go, if you memorize these things, you only need to look back at what you've had previously. So you have like a memorization approach to this. Again, it may complain when I run this, but we'll see what happens. Minimum amount of pence, 48, and that took a tiny fraction of a second, because I'm just running up to each amount less than 48 and building up the results from the ones I worked out previously. That's the kind of thing I'd want them to do at A-level. You're using text-based programming. They're extending the range of algorithms on which they can draw. They're extending the computational techniques which empower them to solve these problems. They're thinking about the efficiency of these algorithms. And you can do the whole thing in Scratch. In fact, so Scratch is a serious grown-up programming language. That thing I just showed you in Python works in Scratch. A little bit slower, but doesn't break the internet when you try and run it. So I think I've illustrated most of these ideas as I've been going through this. The question which I showed you back when we were doing Year 2 math then, about find all of the different ways. I'm going to set that as a little homework exercise for you. How many ways are there to make 50p using modern, current UK coinage? It's a non-trivial question. Thank you so much for joining in and allowing me to pick on you at random points. If you want to see any of these slides again, not sure why you ever would, then the link to those is up on the slide there. Do we have time for questions?
Yes, we do. Thank you, Miles. Any questions for Miles?
Pose for selfies.
We sped through a lot of content.
Sorry.
Miles, thank you very much. You can find more about that on my slides. Okay, Miles, thank you very much indeed.